All right, everybody, please take your seats. And this session is going to be a little different because we have two professors, and professors we like to talk. So it's not going to be, I mean, in a formal way, in a PowerPoint presentation and things like that. So we're not going to be just sitting in the chair and talk like the previous two panels. And I'm Rama Chellappa. I'm a professor of biomedical engineering and electrical and computer engineering at Johns Hopkins. Good afternoon. Welcome to the session on human-centered AI, robotics and interfaces that learn, adapt, and assist. So we have two world-renowned researchers, Professor Rosalind Picard from MIT and Professor Russ Taylor from Johns Hopkins University. What a great pairing. Rosalind is known for her seminal contributions in affective computing. We used to go to a conference that's still going on, Face and Gestures, for a long time. And there's also an IEEE transactions on affective computing and human state sensing and so forth. And Russ Taylor for his contributions in surgical robotics and precision systems. They give us a very natural interfaces to physical systems. It's a bidirectional bridge. So, as I said, they really don't need any introductions, but still, Rosalind actually waited, couple of hours in the TSA line to come from Boston to here? No? Okay, not that bad. Oh, not bad. Very privileged person. So, Professor Rosalind Picard is the Grover M. Herman Professor in Health Sciences and Technology at the MIT Media Lab, where she is founder and director of the Effective Computing Research Group, associate academic head, and associated with the MIT Center for Neurological Engineering. She is author of the book Effective Computing and co-author of hundreds of peer-reviewed scientific and engineering articles in AI, wearable digital health technologies, effective computing, and HCI. She's a co-founder and chief scientist of Empatica, providing FDA-cleared digital biomarkers and medical quality data for clinical trials and research studies. She's a member of the National Academy of Engineering and fellow of many professional societies. And Professor Russ Taylor, my distinguished colleague at Johns Hopkins University, has been directing he's a professor in the Department of Computer Science, secondary appointments in mechanical engineering and medicine, et cetera. And for more than a decade, he has served as the director of the Laboratory for Computational Sensing and Robotics, one of the most technologically advanced robotics research centers worldwide, and an international leader in the areas of medical robotics, autonomous systems, and bioinspiration. Russ was directing an NSF ERC, Engineering Research Center, for 10 years. I think it started around 1996, 97, something like that, assistive robots. So he really is a pioneer, and a lot of the people working in this space, came from his lab. He's a member of the National Academy of Engineering, and of course, he was involved in many other, editorial activities, fellow of many organizations, and so on. So what we are going to do is, Ross is going to first start, 18 to 20-minute talk, and Russ will also follow that with his presentation, and then we have time for a couple of questions, and I will, get them going. So, Russ, please.
I'm going to sit over there so that I can watch Ross's slides and learn.
Okay.
All right.
All right. That's okay.
I mean, that way we can see what she's
All right.
showing.
Yeah, I have a lot of pictures. As mentioned, I am a full-time professor at the MIT Media Lab. I'm also co-founder and chief scientist at Empatica, and I have some disclosures with being a shareholder of Empatica and Smart Eye AB that purchased one of the two companies I co-founded, named Affectiva, and also work with Amazon and Samsung recently. I'm going to start with this old cartoon from Family Circus. I don't know if any of you are as old as I am that remember these wonderful cartoons. Here, Billy got off at the school bus. I don't know if I can have a pointer here. I don't think do I have a pointer? No. So Billy got off at the school bus, the upper left corner, and there he is arriving to his mom in the lower left corner, and she says, "Billy, I've been worried about you. Where have you been?" "Just walking home from the bus stop." We see he's been all over the place. And when Rama invited me, I remember I used to just do computer vision, right? And back when we first met. Since then, trying to understand more about what was going on with the human, I did a lot of work with people with autism and trying to help them communicate emotional information, not just to understand it in others, but to have it understood in them, which they communicated to us was not being done properly. And then along that path, discovered a lot of other things in the data that I was not looking for that are very important medically, like seizures. So I'm going to give you a couple examples and relate these to aging also. First of all, this story started with a little boy who is here looking kind of stressed. We built a wearable sensor that could monitor the autonomic data leaving the lab. Previously, we would wire people up in the lab, get pulse rate variability, electrodermal activity, respiration, other information, but we needed to know, help people communicate this in real life. So we built the first wireless wearable sensors that could gather this data on the wrist in natural life. Here's a picture of one of the sweatbands that was really popular, but inside it is all of this technology. And one day, I'm back in the media lab looking at my data coming back from a boy who borrowed it for his kid brother who is non-speaking with autism, and he wanted to borrow my sensors to see what was stressing out his little brother over the winter break. So I'm back looking at the boy's data, and I see the biggest peak I've ever seen. And I figured the sensor must be broken, because we had tried to create stress at MIT in every way imaginable, qualifying exams, Boston driver stress, other things, and I'd seen some pretty big peaks, but this one topped them all. And so I thought it was a malfunction, but I'm an electrical engineer by training, and my debugging did not show anything wrong with the sensor. So I debugged the old-fashioned way. I picked up the old telephone, called the student at home on vacation. Hey, how was your Christmas? How was your little brother? Any idea what happened to him? And I gave the exact date and time in the data where there was this giant peak. And he said, I don't know, I'll check diary. And I'm like, diary? What's the odds this boy wrote down this time and moment? Well, he comes back, he has the exact date and time, and he says that was right before my little brother had a grand mal seizure. I started to learn about seizures. Here's a picture of some of the data we got off the wrist. The big peak is just the little skinny red line at the left of the big peak is several minutes thick, and that is the duration of the seizure, but there's a giant peak happening even following the seizure, and though that peak is like a redwood tree popping out of a New England forest. The peaks that look low here are usually the biggest peaks of the day. Those are related to slow wave sleep, which I could say a lot more other interesting stuff about. So with the partnership with Children's Hospital Boston, we started, we made sure our sensors were safety certified, and their ethics board added them to an ongoing study with 24/7 around-the-clock monitoring of EEG, ECG, and now EDA, electrodermal activity, on the wrists of patients who were being observed in the epilepsy monitoring unit to see if our signals had anything to do with gold standard measures of seizures. And to my shock, as a signal processing person, nothing is ever 100%, but 100% of the grand mal seizures had a significant response on the wrist electrodermal activity, not in advance of the seizure like we had hoped, but when precisely synchronized with it. This was significant. So my student Ming Zerpo did a PhD building machine learning to combine the electrodermal activity signal with the movement signal and build a lean, what I call today a lean green AI, because it doesn't require us building new nuclear power plants to run this kind of AI. And it runs in an embedded device very efficiently with long battery life. And that is now out there detecting seizures for people in, golly, I should have looked up how many countries now, dozens of countries. I also learned that seizures can be deadly. Usually you're fine when you have a seizure, but I'm curious, how many of you know somebody who has seizures or has repeated ones in the epilepsy diagnosis? Wow, a lot in this audience, good. It's a good sign, because actually those of you who didn't raise your hand probably also know somebody who has seizures, but they may not have told you. I know I was surprised by this when I was sharing with a friend that I was working on epilepsy, a friend who I'd known for 30 years, who I knew had autism and cerebral palsy, and he says, oh, He says, I have epilepsy. And I'm like, I didn't know that. I knew you had CP and autism. How come you never told me about the epilepsy? And he says, I just never tell anybody about the epilepsy. A lot of people need to talk about it because we need to destigmatize it. Anybody with a brain can have seizures, and we have, in the last 10 years, learned a lot more about the progression where you can have a seizure, most people are fine right afterwards, but actually, number 2 cause of all years of potential life loss is deaths that follow seizures where kind of central apnea appears to set in. And they're 5 times more likely to happen with the patient dying if they're alone after the seizure. So find out who you know who has especially convulsive seizures, which are the highest risk, and make sure they know not to be alone when they have a seizure. So this device now is in the field. Empatica got it FDA cleared, first FDA cleared smartwatch to detect seizures. And today, it actually kind of meets the criteria for what people call a software agent, although we didn't present it that way to the FDA originally. It was hard enough to get them to certify a machine learning algorithm. So it's running continuous machine learning in a wearable device, actually in this one too, and it watches for a possible seizure. If you're actually having a generalized tonic-clonic seizure, you're unconscious. So then you can't cancel a false alarm. If you're having a false alarm, you can cancel it. But if you're actually having a real seizure, it will then take action on your behalf. So if I said, give my GPS, here, call these caregivers, it will do that. It will update the diary, and then I can go back and check what happened in the diary and confirm or disconfirm, or also add other events that may be types of seizures that it doesn't recognize, like focal seizures. All right, I started the story with a little boy, but epilepsy diagnoses climb steeply at age 65. So the bottom axis here of this graph is age, and we see a huge hill over there with per 100,000 epilepsy diagnoses happening with late onset epilepsy. By the way, the risk of late onset epilepsy shares a lot of risk factors with conditions like Alzheimer's. For example, the APOE E4 allele is a risk factor. It's also the case that there are symptoms that overlap. If you have a loved one who you're suspecting of, Alzheimer's or dementia, and they're having confusional states, but they really come and go, like most days are good days, and occasionally there's a real bad day and maybe loss of muscle tone, that might be a focal seizure. It can cause symptoms like that. It can also cause falls, like syncope, but the postictal state is longer. And it can also appear to have symptoms like a TIA. And in these cases, a neurologist may even try a low dose of anti-seizure meds and find that the patient is helped by that. This, by the way, is also being recognized in global sets of data as increasing in incidence, prevalence, mortality, and dailies. 193% increase from 1990 to 2021 in late onset epilepsy in people older than 65. With the machine learning wearable continuous collecting devices now, what we can do is get personalized data so the system can adapt and the doctor can adapt the treatment to the person. So what you see in this picture is a piece of data from the Empatica Epi Monitor. Top to bottom is the 24 hours in the day. Left to right here is all the days in April. And blue is when this patient was asleep. You could see here at a glance, this person looks like they have pretty good sleep hygiene, pretty regular sleep. Separately, we do research at MIT with sleep regularity and mental health. So if it's really irregular, that we can't prove causality yet, but it's very often associated with worse mental health. Then we can look at seizure timing relative to these events, and doctors now use chronotherapy and adjust the timing of the medications with the seizures to get better results, best results being, of course, no more seizures. The next best thing people want if they have epilepsy is, well, after I don't want any more seizures, is I'd like to, and I don't want to die when I have one, I want somebody to be there for me, but I also would like to know when it's going to be. So people have been working for a long time on forecasting. There is not yet a reliable or FDA-cleared forecasting system, but there's been a lot of progress lately. And one of the cool things it's able to do is to take data from rhythms, not just circadian, but long-term in these patterns. So we have people wearing these devices now continuously for many years, and we have very nice rhythms. And when you put those patterns together with the physiology changing, those have been shown to be associated not only with neurological events deep in the brain with direct measurement from implants in the brain, but also with these physiological patterns and these manifestations of events such as seizures. So very excited about progress that's steadily being made there. I do believe we'll be able to help give some people early warnings, but it's going to depend on individuals, and we're going to need personalized approvals to do that. Okay, I mentioned this NASA astronaut because NASA picked our sensors for their study of people going to Mars, which I think is pretty cool. Okay, the next thing is what's called a Parkinson's kinetograph, or PKG. So how many of you know somebody with Parkinson's? Wow, this is such a connected audience. Okay, so this is, maybe you already know, the standard state in Parkinson's is low dopamine levels. And when they're low, people say they're off. That can include freezing episodes, tremors, rigidity, slowness, pain, anxiety, of course, when these things happen. And that's interesting. I didn't get to see this slide before, so it doesn't look right. Sorry about that. What you should see is a white sinusoid and a green section that says on time. And what we're trying to do is get the dopamine levels to get up to where the patient has what they call on time instead of off time. It doesn't mean they're on time for this meeting, but if you can't move, you're likely to not be on time. So helping them move, right, and be able to function in a normal way. Let's see what happens here. Sorry, this picture is not so good either. But if you imagine those white sinusoids going too high, outside, higher than the green on time, you get into a state of what's called dyskinesia. And that is unwanted. It is not caused by the Parkinson's. It's caused by the treatment, the drug, something like levodopa or another treatment. And that's where you have unwanted erratic movements like the jerking or twitching. So how does a doctor know how to titrate the right medicine for this? Well, what they've been getting great results with is they put a PKG, a Parkinson's kinetograph, on the patient for about a week, and this one I'm wearing here records 3-axis accelerometer, ambient light, gyroscope, magnetometer. The battery will last about 2 weeks, and then AI is used to map these parameters to the data that doctors are very interested in tracking. And then doctors use that to adapt the medicine. I seem to be missing something important there. All right, well, so some of these key features, again, are the dyskinesia, the unwanted movements that happen when your dopamine is too high. They can also happen due to other things. I've heard there's white coat dyskinesia, just for coming in the doctor's office. Bradykinesia, just like with bradycardia, it's too slow. Your movements you're not moving as fast and as fluidly as you'd like to. Tremor, related to the Parkinson's when you're in your off state. You could tell the difference between that tremor and tremors from dyskinesia. And gait changes or freezing, sleep changes that are very often affected in Parkinson's and lots of other aging conditions. And then doctors adjust the medication with this, with the goal being to reduce that off time, increase that on time. And now that you can not only quantify that, but you can actually see where it's happening. So we give doctors this big picture. I'll zoom into a little bit of this. Let's zoom in. So the doctors get a summary of how much bradykinesia that week, how much dyskinesia, how much severe dyskinesia, is this new treatment moving the patient in a good direction with more of that white zone in the middle, or too much of that off time in the turquoise there, or too much of that dyskinesia in the yellow-orange. The doctor can also see exactly where that's happening. So on the bottom here is the off time. On the top, that orange is the dyskinesia. And doctors can see, is it happening with peak dosing, or is it happening with something else in the patient's life? Do I need to treat them differently at night or in the morning? And so when doctors measure this and get that data and change the way they treat it, looking at tremors, looking at immobility, then, and also giving patients medication reminders. When they do that, then they get a lot of really nice results. And I won't go through, but there's over 90 studies now that are validating not just the accuracy of the bradykinesia and the dyskinesia and the tremor and all these things that are important to map the sensor data accurately to the doctor's descriptions of these important symptoms. But there's also now studies showing that it improves the classic measures that they monitor in Parkinson's care. So people are actually scoring better on things like the UPDRS or the Epworth or some of these other very important scales. Also, I heard Mary, the nurse, talking earlier about caregiver burden, which we know is really heavy also, and it was neat to see this result in another study where the caregiver burden was also reduced significantly. Since mental health of everybody in the family is important, anything one can do with the technology to help not just the patient but the whole system around them, we think is really worth aiming for. Also, a big study in the UK showed cost effectiveness, significant cost effectiveness per patient, so that's hopeful. All right, finally, a couple minutes, I will just end with a couple slides, one on some work we're doing in our lab with sleep that we think is important for all kinds of people, not just Parkinson's and epilepsy patients, but all of us, and also is contributing to improving forecasting for different kinds of events, that whether it's seizures, migraine, off time, whatever, we think we need to get this whole picture and understand how these components interact. So here's one piece of recent work from our lab. This is work funded by Samsung with using their consumer watch to measure the photopic illuminance in daily life. We also had a gold standard sensor measuring melanopic irradiance. We built an algorithm to estimate the circadian phase, which the gold standard measure of it is from melatonin in your saliva. Take lots of measures of that with dim light. So people went through this extensive dim light melatonin procedure. We built the model, and we showed that we could get significant improvement over the usual way of estimating phase in the wild, which is just 2 hours relative to your normal bedtime here. That's the baseline measure right here. And so now we're using these different physiological rhythms to tune up people's performance in lots of different health conditions, and getting some super exciting results there. Also, especially in the mental health space, health and well-being, which, again, proving causality in a lot of things is still a little tricky because there are many variables. But we're finding a lot of significant associations there that become candidates for causal manipulation. Thank you so much, and here's how to find me if you have questions we can't answer during the panel today.
Wow, that's a hard act to follow. Let's see, what do I do now to get to my talk? Oh, what, there. Okay. Well, again, thank you for giving me the chance to talk to folks here. These are my usual disclosures. And start out with, what do we mean by robotics? Well, basically, robotic systems couple the physical world to the information world. You can sense the world, and you can act in the world. And fundamentally, we're dealing with a system science that combines many, and again, we don't have a pointer, but many of these different technologies all together, working together to do something in the world. And my work, actually for my entire career, has focused around this picture of three-way partnerships between people, all this good technology and information to provide intelligent action, to do useful things in the world. Well, one thing is, if we have all this information, we don't have to throw it away. We know what we did, and we know the outcome. And so now we can begin to use that information and using, we called it an IBM process learning, but it's various sorts of machine learning methods to improve our processes for future cases. Well, why do I want a partnership? Well, I think it's because people and machines have different capabilities. With all of this AI, there is increasing overlap, but machines have better precision, other things that people cannot, and what we want to do is get the advantages of both in partnership. There's a long history of robotics doing useful things. My early work at IBM and thesis work. On the right is an automation system we developed to extract the salivary glands from mosquitoes in order to develop a malaria vaccine. Embodied AI, we have a long history of working in the world. There are systems like from the early 1970s. On the left, that is actually playing is a system called Shaky, but we're seeing lots of examples from a long evolving of more and more capable systems of working in the world, although occasionally there are lacks of understanding still. If I think about this partnership, you talk about levels of autonomy, there are really two key questions. First is, how can I tell the machine what I want the machine to do in a way the machine understands it? And then, can I trust the machine to do what the machine is supposed to do with me and be very sure it won't do what I don't want it to do? They're not teenagers. What can I say? If you're going to have these partnerships, even between people, you need some shared situational awareness, some common understanding of what the task is, what the environment is, what the results of actions are. And more, I've come to believe that this is best thought of as a digital twin, some kind of a real-time simulation model that runs concurrently with the task and can be updated with what you're seeing as you go on. Well, how does all that relate to healthcare? Well, first, as we all know, there's an increasing demand, and it gets more and more expensive when you get to be my age and beyond. Second, there's a real gap between caregivers that are needed and what we already have, and this gap is expanding, it's continuing. So can we use machines to help us? Now, my song and dance is that robotic assistants can really help us, but I think it's important to look at the entire treatment cycle: diagnosis, treatment, recovery, ICUs, care, clinic, all the way to the home. Now, my main focus for about 30 years has really been on robotic systems in surgical applications, where the machine has greater precision. It often is, you can have high dexterity inside the body, access inside the body, and other things that people don't have. They don't care about x-rays. AI systems are enabling more and more intelligent assistants. Also, you can couple additional information. And one other thing, we're beginning to see, and I think there's a big opportunity for scrub nurse type capabilities. Well, research challenges are common, I think, and here we've had to face them. Real-time perception. How do I keep that model up to date? How do I communicate between, in this case, the surgeon and the robot? Action planning and control preoperatively, intraoperatively. Crucially, how does the machine recognize something that it hasn't seen before? These learning networks don't have a sense of humility. They don't really know what they don't know. And obviously in surgery, you can kill somebody if you do the wrong thing, and safety is very, very important. Well, I've had a long history in this, and these are some of the applications that we see around the world. A lot of mine. My initial system actually was a system for hip replacement surgery, which us old guys have. And there it was pretty much autonomous. And now for soft tissue surgery, my colleagues at Johns Hopkins have recently been able to do a simple gallbladder surgery on animal autonomously. So there's progress in this area. I could talk all day. I'm a college professor. But what I'd really like to do is talk about what I see as the future. And if we think about ICUs, well, a robot doesn't get disease, so you can go into that environment. Some of the kind of things that potentially we can do is operate equipment, stocking, replacing consumables, changing IVs, all inspection monitoring. We can't do all those things yet. We're beginning to do some. Challenges are very much the same as with these surgical robots. There's slight differences because of the environment, but one of the things I'm emphasizing is a continuity of capability for these human-machine partnerships. Well, I got very interested in this back during COVID, and one of the things that we did is we developed this little teleoperated robot that you would clamp onto the control screen of a ventilator, and this meant that you could operate the ventilator without having to go into the care room and put on all that protective equipment. And so it was a very nice little robot. It had visual servoing and a bunch of things like that. But you say, wait a moment. It's all a computer. Remotely, we should be able to control that through the network. And eventually you will. But we've also been working on ways to make the device itself smarter. And again, the key is actually to maintain a real-time digital twin model of the patient. And crucially, you should be able to see when the patient is not responding the way your control algorithm expects and go call for help. And this is just a block diagram of that. At the same time, I really began to think a lot about potential uses beyond that. And among other things, rather than clamp a robot for each piece of equipment, have a more mobile robot, perhaps with a couple arms and a tool belt and so forth, that could do many of these things. And I think we're beginning to see that. A lot of those same capabilities can also be used in hospital care rooms. And again, if you look at the requirements, the challenges to make these systems highly effective, there's a remarkable continuity of the underlying issues. So here's one system that is commercially been commercialized as an NSF-funded startup. This little system is basically for hospital logistics. It's sort of a nurse's aid. Has an arm that can be used. It can open a door, which is one of the important things. And already does a lot of these support tasks. However, there is a real potential if you can equip this system with higher dexterity and greater ability to perceive the environment and to even be more interactive with the nurses. You can do a bunch of things. It can do more tasks. It can actually, potentially, you could send it off on an errand to take a look at Mrs. Jones there in the care room or the ICU and report back. We mentioned patient handling. That's been a major interest in Japan, especially for many, many, many years. This system has been goes back to 2009. I think this is about a more recent version. But what we're seeing here is this robot is called Robotics. It's very strong. It can lift 100 kilograms. They carefully worried about making it seem friendly so the patient wouldn't be terrified. Well, that's a very important thing. We're dealing with systems that have to work with patients and with other people. Again, there's great potential to take this kind of capability, integrate it into rehabilitation applications, and also integrate into cluttered environments in the home where you don't want the robot tripping over the cat. And this, again, requires really to be robustly there, great improvements in our ability to perceive in real time and react in real time. So I mentioned rehabilitation. And again, I'm using a few examples of things that people are doing today. Again, in rehabilitation, a lot of those same capabilities, dexterity, strength, mobility, and a crucial one is patience. That you have to do something very, very repetitively, often many times. Just as what Roz was talking about, robotic systems, the AI can enable more or less automated progress assessment. I haven't looked deeply enough to know how much they do now. Also, inspection and monitoring of care, and perhaps making the rehabilitation more adaptive. Again, the fundamental challenges with some differences in detail are basically the same throughout this entire continuity of care. Here's an example of one system. This just basically, the robot will work a patient's limbs, and the nurse is kind of hand over hand guiding the robot to show the motion that needs to be repeated. I think there's a great deal of potential here to make this system more adaptive. I'm not sure how much they actually do, but you can automatically assess progress. You can adapt how hard you're pushing. And adaptively, from what you're seeing, use the AI system to help the rehab person optimize the rehabilitation plan. So the robot is just one device that can be used to assist in providing care. Well, okay, what about an outpatient clinic? Same sorts of things. Dexterity, telepresence, the ability to give you remote access. Some of the things that AI people are talking about are just the intake, providing the initial questionnaire. That would also be very important often in an emergency room. And the AI potentially should be able to help do kind of routine procedures. Here, human-machine dialogue is a major consideration, depending on what you want the machine, and perception. All these things about seeing an aspect of the patient are important, even for screening and triage. But the ability to have intelligent communication, even beyond this sort of scripting we heard about earlier, is, I think, just extremely important. Here's one really interesting example of what is already there. This is a system for screening patient with for arthritis. So you're seeing the guy comes in, he's identified himself. Now he's put goo on his hand, and now the robot uses computer vision to find his hand, then comes over and conducts an ultrasound scan takes 2D ultrasound probe, moves it around, and gets scans where limiting force, and then they have some AI capability in this initial commercial system to assist with diagnosis of hand arthritis. Well, where can this go? Generalized ultrasound scanning with vision and force-guided control of the scans. There are a lot of other examples that we've been exploring at Hopkins along this line, but what you would really like is the human to be able to come into the environment and, or you get a sort of a general, I need a scan. The robot looks at the patient and is able to set this all up autonomously to give what you want. If the AI can also, if you can analyze what you're seeing in real time, you can realize, hey, I better go back and look more carefully someplace. So again, I feel like I'm pitching the future more than bragging about the present. If we look at home care, there are huge opportunities here. Very similar set of requirements. AI enabling companionship and communication is, however, really important, and systems here should also be able to help with activities of daily living. If I look, this system I think is just extremely cute. This is a robotic pill dispenser. Now, I met someone here with a more elaborate version, but basically what that system does is you load it up with your doses. It has face recognition, voice recognition, some video conferencing, knows when you missed a dose, and you can use it somewhat for general companionship. Well, if you could integrate this with more vital sign sensors, that would be good, and those are within the capabilities today. In interacting, can you detect visual and conversational symptoms of stress and disease without Roz's attachment? And finally, integrate this with your home healthcare robot, which greater mobility. I should mention in the home, what you really need is probably legs. You need all these others, you can roll yourself around, but here, again, you don't want to trip on the cat. And I'm running out of time, so this is basically a fetch and carry robot. It shows, again, this is a long-standing effort in Japan. Coming back to this picture, this is a systems technology. Robotics are systems. A lot of the capabilities that we're developing in one or another of these application domains should be transferable to others. And I think it's important to take a comprehensive view of the evolution of the entire field. If I look at research issues, I've got 20 seconds. You need human-machine interpretation. You need to be able to assure action. Again, information, I believe that you need to be able to develop online modeling, or again, look at the whole treatment cycle. There are key challenges across the board, and I can elaborate on these, but this really requires a team of all of us, and the real payoff is really improving the quality of care for an aging population. In fact, for everybody. It's not just old folks.
Thank you. Take a seat. Right.
Okay. And Roz may want to come up too.
Thanks, Russ, for those two wonderful talks. Russ mentioned perception and action. Robots have come back now with AI because they're actually test beds for AI. Right? I mean, we can put them, like wearables are also coming back because of that. So my first question would be bridging perception and action. This is something that computer vision people and roboticists have worried about for a long time. So how do we close the loop between effective sensing, that is Ross's stuff, emotion, cognitive, and other perception tasks, and real-time decision-making in robotic or assistive systems without introducing instability or overaction?
With that, Roz, while I think.
Sure. Let's see, is this on? Yeah, this is
on.
on. Okay. Actually, I don't know if people were here for the earlier ARPA H person who said, he's a physician and said we don't need doctors anymore. Rahul, I think was his name. I don't know if he's here. But I think we do need doctors and professionals and experts. And I think we need to design the systems with them in the loop at strategic points, at least for quite some time until we really build trust and confidence in the fact that the actions being taken are the right ones. Like, I think as I look at now what we can do and what the doctor's doing, my engineering mind says, oh, feedback loop, automate that. But when you actually go into the wild and you look at how complicated it is and all the side contextual things that a smart person looks for and watches for and says, yeah, well, in this case, the data say that, but here's this other thing that the system hasn't seen data on yet, so it doesn't know what to do. I still think we need that wise human oversight in a lot of these places.
I think it's going to be a very long time. A surgeon colleague pointed out that a 4-year-old has had something like 4 petabytes of training data. I think that the key is to focus on progressions of applications that are always hard and useful rather than just cool. And I think you'll see what we call in task autonomy, systems where the robot will be contributing something that it can do. And as your perception gets better and your ability to reason gets better, and they can become more and more capable, but I actually don't see any time, certainly in my lifetime, where they'll completely take over the whole robo-doctor. So I think that's really important to think about progressions of capabilities and understand at each step what the relative roles are. And you need for that some shared understanding. I personally believe also that you can't just rely on a bunch of gains down in a neural net as sufficient. You need a model that is explainable and somehow also tied to the physics of the real world.
Yeah. So my next question would be the balance between assistance and autonomy. While we are striving to have robots, to assist people, but where do you draw the line? How much assistance and how much they want to be autonomous, and what are the push and the pull of these two important components of caregiving?
Yeah. Well, that kind of follows on what I was saying. I think in each case, the robot needs to be able to do something that the surgeon cannot do, or the human caregiver cannot be. Sometimes it's just to be available. In other cases, certainly with surgery, it's somehow the robot has some higher precision, and it can rely on its sensors and perception to do some piece of a task better than the surgeon could do.
Yeah, and the line is always moving as the technology
that's the point.
advances. So you may know some people who have implants in their brain that can detect unusual electrical activity that might be a seizure and add stimulation to it in a way that sometimes squelches the seizures, but doesn't work most of the time for most of the seizures. So using that in conjunction with something else that gives people more control, more understanding. I think in general, anytime we can reduce somebody's uncertainty about events, there's some exceptions, but generally giving them less uncertainty and more control over a situation reduces stress and improves well-being. That said, I don't know how many of you have used one of these well-being apps that like tells you to do things that you don't want to do, right? Like, so we've had people, we do a lot of N of 1 studies where people are trying to figure out what's optimal for me, and I want to go to bedtime, have this smart bedtime on this schedule, and you're motivated, you want to do it, but you don't do it, right? And the autonomous system can't force you to go to sleep, right? It can force a message that's super annoying that makes you never want to use the app again, but it can't actually force human behavior.
I relate to that. My well-being app says I should not eat cookies, and I completely ignore that.
It's also
My
like
last
New
question
Year's
would be
resolutions.
personalization versus generalization, right? We do want the models to be very personal to just know what the person needs. So how do we design systems that learn deeply personalized models while still being robust, scalable, and clinically or socially deployable? That's, again, a compromise, all this.
Wow.
Yeah, well, we've learned a lot from with new ways to do machine learning, where you can take heterogeneous data from lots of people and cluster subsets and multitask with different groups of people and lots of other techniques that improve without having to just have all the data on one person. Although, like our best machine learning mental health prediction results still involve having a lot of past data on a person before we predict their future states. And same with the seizure stuff now. There still is a lot we learn from other people besides that person. So we build these kind of big baseline population models and then try to forecast individuals. I have to say, too, my students have been trying really hard to get the equivalent of the large language models, the large sensor models, to do well. And while they do really well at using, like 8 orders of magnitude more parameters and equally many orders of magnitude more energy, so far they haven't moved the needle on the accuracy of what we're trying to predict. So they do a huge amount more work, and they're not actually improving our prediction results.
There are engineering and research to improve capability. I think the question of assurance and trust is really important. However you're trying to help the human has got to trust you to do what you want it to do and not do what you don't want it to do. And certainly when I deal with surgical applications, that becomes just absolutely a question. No surgeon is going to let a robot do something if he thinks it's going to sever the facial nerve, as a simple example.
So with that, let's thank the speakers. Thank you very much.